So okay, good evening. So we meet again for face-to-face class. So as we have discussed earlier, so we will do face-to-face class on Thursday and also online class on Friday. So I hope you all can just follow. Why I'm emphasizing on face-to-face class is because some of the terms I need to explain. Okay, sometimes your concentration in online so will not be that good like how you are experiencing in the class. So I hope you all can it's okay for you all. Okay, so today we will continue with chapter 4. Okay, so it's one of important topic, the second law of thermodynamics. Okay, so if you can recall, so we have 4 laws that we need to understand. Okay, first is zero law of thermodynamics. Okay, so this is your number 1. Second is first law of thermodynamics. Then we have second law, and we have okay, so we have 4 laws of thermodynamics so involved in this subject. Okay, so I hope you still remember zeroth law of thermodynamics. So do you still remember? Anyone? So zeroth law, I think we studied in chapter 1 or chapter 2. Okay, beginning chapter 2. Okay, so what is the application of zeroth law? Simple application for you to remember. So something that you used always. Thermometer. So when two materials or two substances are in contact, okay, in contact or in the same environment, so they will have a isothermal condition, and when you have another substance touching either one, so it will have the same, so it will have the thermal equilibrium. So that is what we call as zero law of thermodynamics. So we have studied first law of thermodynamics also. So what is the first law of thermodynamics? Do you still remember? So all these are very common questions. So hopefully you all remember. Okay. So first law of thermodynamics. So energy cannot be created or destroyed. Okay. So whatever energy, it can be thermal energy or whatever energy, potential energy, kinetic energy. So all these energies we have studied. And this energy cannot be created or destroyed. It's already available, so it only can change forms. Okay, one form to another. So potential energy can change to kinetic energy. Kinetic energy can change to heat energy. So the energy will change form, but it cannot be destroyed. So that is first law of thermodynamics. And today we will study about the second law of thermodynamics, so which we will be covering. So it can be, if you see the lecture note, so it can be a bit confusing because too many things. So because initially we have studied all this basic concept, then suddenly something heavy. So in this chapter 4, so but as usual we will go slowly. We will go slowly so that we will understand. Okay, so just flow with me. So try to understand the concept. Okay. Okay, so this chapter will be covering 3 sub chapters. So the first one is thermal energy reservoir. Okay, what is reservoir? Okay, what is reservoir for your layman term? What is reservoir? What we call reservoir always? Okay, bahasa Melayu, what we call reservoir? Bekas. Okay, So bekas is container. Okay, so it can be like container, but it's very big. Okay, reservoir we always call like dam. Okay, empangan. So it's a reservoir. It's something very big that can contain certain things. Okay, so in practical word, so it's a bigger container. So bigger container that you cannot contain. Okay, so you cannot have for yourself. It will be very big. So thermal energy reservoirs. Okay, so there are later we will see what is thermal energy reservoir. Then we have heat engines. So we have refrigerators. So I believe you all know. So what is refrigerators? Okay, the fridge in the house. Okay, and all the similar kind of systems. And we have heat pumps. So all these are related to second law of thermodynamics. Okay, then we have another concept called reversible, irreversible processes. Okay, then we have Carnot cycle. Okay, so today we will only see a fraction of part 1. Okay, then we will continue tomorrow. Okay, so as the introduction to the second law, so we will learn a few basics behind the second law before we enter to what is second law. Okay, so a process must satisfy the first law to occur. So first law meaning first law of thermodynamics. So what is first law of thermodynamics? Again, so energy cannot be created or destroyed, it only can change form. Okay, so a process must satisfy the first law. So meaning this is the first prerequisite. So a process must satisfy this first. So this is first condition. Okay, so satisfying the first law alone does not ensure that the process will actually take place. So meaning, so first law alone is not sufficient, so not enough for a process to complete. So meaning you need to have additional things. So additional thing as a condition for the process to actually take place. Okay, so that is what we will study in second law. So meaning, so you can see one example. So you have a hot coffee. So let's say you have a hot coffee and you have a cool room. Okay, like this room. So let's say you put a hot coffee on the table. Okay, what will happen after some time? So the heat from the hot coffee will be transferred to the environment. So the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. Okay, so this is fulfilling the first law. So hot coffee will lose energy, okay, as a heat, and the environment will gain. Okay, so it will gain. So that is what is mentioned in the last line. Okay, then you can see. So will this thing happen? Will this thing happen? So you have a cold room and you have a hot coffee. Will this thing happen? Heat transfer to? No. So unless you have some certain condition that assists the heat to transfer to inside, it cannot happen naturally. Okay, so it cannot happen naturally. Okay, so this is another example. Okay, let's say you have a system. Okay, with the weight. So let's say the weight due to gravity goes down. So it will twist the system, just like a turbine, and heat will be generated and will be kept in this system. So meaning here, so you have a potential energy of the mass. So as it goes down, it will decrease, because why it's decreasing? So as it goes down, why it's decreasing? Potential energy. Why? So you can just give any answer. I won't score. Yes, potential energy is converting to kinetic energy. So the potential energy is decreasing because it started to move. Once it start to move, velocity will increase. So kinetic energy will increase. So meaning potential energy will be converted to kinetic energy. So that is the reason why the potential energy is decreasing, and the internal energy of the fluid increases. So as it moves, so the internal energy, so this is a closed system, so the internal energy will increase inside, because there's a movement, so there's a heat transfer. So we know when heat is entering a system, so automatically the molecules inside will start to move, because as you are giving heat, so it will start to move more vigorously. So that is the reason why the internal energy increases. Okay, so for your test, so your questions will be like this. So I won't ask a simple question. So why the potential energy decreases? Why internal energy increases? So you need to know. So that is what you supposed to. That's the cause outcome of the subject. So you need to understand what is happening at the back. So that's why initially also I told everything also I will ask why. So we have 2 questions in final exam. Sorry, midterm exam. So midterm exam will be after your semester break, mid-semester break. So you have ample of time. So I don't know about your other subjects. So you need to divide your time. But for thermo, so we will be having 2 questions. Okay, so later I will just give you the structure. Okay, and we have 4 parts. Okay, question 1 you have part A, part B. Question 2 you have part A, part B. So 1 hour. Okay, 2 questions, 1 hour. So the questions will be like this. Something that you need to think and you need to answer. Okay.
Why potential energy?
So potential energy decrease because the potential energy here, initial potential energy is converting to kinetic energy, right, as it goes down. So similar like the rock on the cliff. Okay, I think you still remember chapter 2. So the rock is falling down, so potential energy will be converted to kinetic energy. So the questions will be like this. I never say the question is this. It will be something like this, something that you need to think and answer.
Then the energy is similar to the kinetic energy.
So once the potential energy is converted to kinetic energy and this thing is rotating, so heat will be generated inside, and because the heat is entering the system, so internal energy will increase. So similar like molecule. Okay, so let's say it's going up, potential energy, kinetic energy is converted to potential energy. So this is not really possible. So because there are no mechanism for it to move out. Okay, so similar like what I said. So it will be from a higher order to lower order. Okay, always it will be like that. Okay, so processes proceed in a certain direction and not in the reverse direction. Okay, so this is possible, but these two are not possible unless you have something, you assist the system. Okay, so this is possible if this cool room, you put this hot coffee in a microwave in the cool room, then you heat up, then the heat can enter inside. Okay, 70 degrees can become 100 degrees with the assistance. With assistance naturally cannot. So this is also the same. Okay, once the internal energy increases, so you need to do something in order for the work to be done. Or the heat to be released. So unless it happens naturally, so the internal energy cannot decrease. Or you need to do something inside to make the internal energy decrease. So it cannot happen naturally. Okay, a process cannot occur unless it satisfies both the first and the second law of thermodynamics. Okay, so as we know, first law must be satisfied, but it's not sufficient, so it need to be together with second law for a process to complete. Okay, so we will see about thermal energy reservoir. Okay, reservoir is, what is reservoir? Hypothetical body with a relatively large thermal energy capacity, so mass and specific heat, that can supply or absorb finite amount of heat without undergoing any changes in temperature. So meaning, it's like a power bank. So imagine like a power bank. So you can put a lot of battery. You can charge. You can keep on charge. So when you are charging the power bank, so it's not expanding. So it's still the same size, but energy is going inside. Okay, so it can save a lot of things inside. Okay, a lot of energy inside, and when you in need, you can use it. Okay, so reservoir is like that. So it's a body with a relatively large energy capacity. Okay, so in this case, thermal energy reservoir, so it's related to thermal energy. Okay, so thermal energy is a, so let's say the reservoir, water dam outside, what it can store. So what water dam, okay, Empangan Timataso. So we have a Timataso dam in Perlis. What it can store? Water. So water dam, water reservoir will store water. So thermal energy reservoir will store thermal energy inside. Okay, so power bank can store electrical charge inside. So you can use it at any time. Okay, so this is on the physical side, and it must be supply or absorb finite amount of heat without undergoing any changes in temperature. Okay, so when you are charging, so it's not supposedly to increase in temperature. It must have a mechanism to keep everything inside, because if you are charging and at the same time you are giving the power out, so it won't store anything. So imagine you are charging a battery, your phone. So charge immediately. You are watching something, then the battery will not increase unless you just keep it in the electrical source for some time. So the percentage will increase. So if you keep on using as you are charging, so the energy cannot be stored inside. Okay, so that is the explanation for thermal energy reservoir. So in the exam, let's say I'm asking, explain thermal energy reservoir. So you no need to write everything here. You just tell based on what you understand. Okay, so if you can draw something, so normally I will mention there. So please explain with suitable aid of figures and sketch. So make sure you draw something that I can relate, I can understand. So if I can understand what you are trying to say, I will give marks. So it's not based on answer scheme. Okay, so that is the advantage of this subject, and it can be disadvantage for you also if you don't know how to explain. So if you know how to score marks, so I will give marks. So I will just want to test whether you understand the concept or not. Okay, so large bodies of water such as ocean, lake and rivers, as well as the atmospheric air, can be modeled accurately as thermal energy reservoir. Okay, so in a real life, in an environment, so we have ocean. Okay, what ocean is keeping? Okay, ocean, what is it's keeping? Okay, salt water. Okay, so it can be water. Okay, lake, the same. You can store a lot of water. So rivers is a dynamic form of reservoir, and we have atmospheric air. So the air surrounding, just keeping all the nitrogens, oxygens, so everything for our daily use. Okay, so our daily breathing. Okay, so all these are considered as a thermal energy reservoir because it can contain the energy. Okay, two-phase system can also be modeled as a reservoir, since it can absorb and release large quantities of heat while remaining at constant temperature. So this is two-phase system, meaning like power bank. So you are charging from electrical source to power bank for one phase, then from power bank to your phone. So that is second stage. So if the system, the reservoir, it can be considered as a reservoir if it can absorb and keep, and the temperature should not be increasing. Okay, so if it's not increasing, it can be it can be considered as a thermal energy reservoir. Okay. So the temperatures of most industrial furnaces are carefully controlled, and they are capable of supplying large quantity of thermal energy as heat in an essentially isothermal manner. Okay, so what is saying is an industry. So let's say, so I believe some of you already have some industrial exposure. So if you come from diploma background, so if you are coming from other mediums like matriculation, I'm not sure about foreigners maybe. You have any industrial experience before this? Industrial attachment, no? Okay, so but soon you will go. I think third year. So before you entering your fourth year, you will go for industrial training. So you can see in the industry. So we will have this industrial furnace. So industrial heat generators, heat reservoir, so which can keep a lot of energy. Okay. So the temperature of most industrial furnace, they have the temperature controller. So it will, even though the temperature inside is very hot, so they will have a temperature controller to moderate the temperature so that it won't be harmful, and they can supply large quantity of thermal energy as heat, because most of the system, most of the machines in the industry, it requires a lot of thermal energy. So when it's needed, they will supply from the furnace. Okay, so and it must be supplied in an isothermal manner, meaning the furnace temperature should not really affecting the other systems. So it must contain, because as I say earlier, so if it's containing the thermal energy, at the same time a lot of thermal energy is escaping from the furnace, so it cannot store a lot. Okay, the efficiency of the system is not good. Okay, so any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbs can be modeled as one. Okay, so it can be any physical body, so anything physical, and it has a lot of capacity to store. Okay, and it can store as well as supply when needed. So you can consider as a thermal energy reservoir. Okay, so there are two terms involved. The first one, source. Okay, so a reservoir that supplies energy in the form of heat. Okay, so in this throughout this chapter, so we will see this term sauce, not chili sauce. Okay, so not chili sauce or not tomato sauce. Okay, so this is the source. Source meaning the origin. Okay, the origin of the energy. Okay, so the reservoir that supplies. So if the reservoir is containing something and it gives out energy, so we call it as a supply, source. Okay, a source. So source is a reservoir that supplies energy in the form of heat. Okay, so if your production line, so let's say in the industry you have a production line, your production line so needs heat energy. So from the reservoir it will supply heat energy, so it will be considered as a source. Okay, so thermal energy source, so it will supply heat, so the direction will be from the source, so the arrow will go out. And then we have another term called sink. Okay, sink, a reservoir that absorbs energy in a form of heat. So earlier I told you, so let's say, so you have a okay, so reservoir, so it can take heat as energy and it can release. So it has two functions. So this is function 1, so this is function 2. So if the heat is entering the reservoir, so this is coming from another source. So this is a source. So this is a sink because sorry. So heat is entering. So the reservoir is acting as a absorb. So this is a sink. Sorry. Okay. So this process is called a sink because the reservoir is absorbing energy. Okay, absorb and save. So this is a source. Sorry. So because from the reservoir energy is going out, it's supplying. Okay, so that is the term. So we have two terms that we will use throughout the subject. Okay, so source, supply energy, sink, absorb energy. Okay, so it will be like this. So thermal energy sink, so heat is entering. So we are learning a few terms that we will use throughout the chapters. So thermal energy reservoir are often referred to as heat reservoir. Okay, so another name, thermal energy reservoir also can be called as heat reservoir since they supply and absorb energy in the form of heat, because it can do both. So it can supply as well as absorb. Okay. Okay, so heat engines. Okay, work can easily be converted to other form of energy, but converting other forms of energy to work is not that easy. Okay, so let's say you are doing something. So you are doing a work and the work is converted to heat. It is something that happens naturally, easily. But you are doing something in order to convert it to work. So meaning heat want to convert to work, it is not so easy. So that is what the term is saying. So normally what we will do, so normally when there is a movement, work is done and it will generate heat. So it's something that happen naturally. But without having any work, for it to convert it to work is not easy. So that is what is saying. So converting it to work requires the use of heat engine. So you need to have an assistant. So assistant called as a heat engines. Okay, so heat is considered like a heat generator. So heat generator will help you to convert the other forms of energy to work. Okay, so heat engines can be characterized by the following. They receive heat from a high temperature source. So you have a high temperature source. Okay, let's say this is 500 degrees Celsius. Okay, so you have a heat engine here because we know that heat engine will help you to convert heat to work. So heat to work, because it is not easily done by naturally. So you need to have the heat engine. What it will do? So high temperature source, okay, let's say 500 degrees Celsius, it will give. So heat engine will receive Q in. Okay, Q in because heat engine is receiving. So this is a source. So this is a sink. So what it will do, once it enters the heat engine, okay, a work will be going out. So the heat will be converted. So mostly will be converted to work. Okay, it will do something, a mechanism inside to generate work. Then a portion of the heat will be released to the sink, okay, because sink will absorb. Okay, so that is the concept of heat engine. So they receive heat from the high temperature source. So it can be solar energy, it can be oil furnace, nuclear reactor, so which can give very big temperature. Okay, they convert part of the heat to work. So like this, so it is converted to work, usually in the form of rotating shaft. So normally it will be rotating a shaft. So heat will be entering and it will create a flow, and the flow will move the shaft. It will rotate the shaft. Okay, So a portion of the heat will be rejected to a low temperature sink. Okay, sink is like how in your house you have a sink, so you will throw whatever dirty water or what, so you will throw. So the same concept. So whatever is rejected, uh, it will be released to the low temperature sink. So it can be at atmosphere, so a river or etc. So but normally we will be careful if we want to release it to the nature. Because of environmental consideration. So but if it's only water, it's not uncontaminated, no chemical, so then you can release it, or it will go into environmental control. Okay, and it will be operating in a cycle. So that is what we call as a heat engine. Okay, all these heat engines are related to second law of thermodynamics. So we will see that part tomorrow. So today I'll just giving you some introduction. Okay, heat engines and other cyclic devices usually involve working fluid to and from which it is transferred while undergoing a cycle. So meaning, so you will have working fluid inside. Okay, working fluid. So fluid, we know it can be gas or liquid. Okay, so now usually it will be liquid. So it can be oil. So it can be maybe water. It also can be a gas. Okay, so it will have a working fluid. So similar like our car. Okay, so for your engine to work, so you need to have the engine oil. You need to have a gear oil. So brake fluid, so everything you need to keep on maintaining. So keep on maintaining, because it is assisting you in the conversion of maybe the heat to work. Okay, so heat to work, because so when the gear is rotating or the piston is moving, so it is actually generating some work. So that's why your car is moving. Okay, so that is something that is related to heat engines. Okay, so the work producing device that best fits into the definition of heat engine is the steam power plant, which is an external combustion engine. Okay, so if you know police, we have a steam power plant. Okay, so if you are familiar with Kuala Police area, so you can see there's a steam power plant there. Okay, so I heard that so they are closing down soon, because so I'm not sure what's the factor, but we have a steam power plant. So what will happen in the steam power plant? So we have a boiler. Okay, so boiler, so is considered as a energy source. So maybe you have a furnace inside, so which will boil and increase the temperature. Then it will be supplied to a turbine. Okay, turbine, because of the airflow and the construction, because once the air is entering here, so it will push the turbine to rotate. So when it rotates, work is done. So it's going out, and it will be going to a condenser. So condenser will cool the hot fluid into cold fluid, and it will go in a cycle. So pump will help to create a flow. So here it will go out to energy sink such as atmosphere. Okay, that's why you see normally companies, the industry, they will have like a pipe to release the gas to the environment. Okay, so normally it will be water vapors which will be released to the environment. So this will be a system, and you will have a system boundary, because all these are operating. Even though you have 4 systems, boiler, turbine, condenser, pump, you have 4 systems, but this is considered as a closed system, because it is only moving in the same cycle, in the same system. So the energy is not going up. Okay, so you can see all these things. So I think you are familiar with this. Q in, So heat is supplied to the steam, then work out so by the turbine, so Q out from the condenser to the energy sink, and work in because flow is entering, so work is done to the pump, and pump is doing work again, so it will go in a cycle. Okay, so we can see, so heat engine, so we have work out, okay, and at times it will be a part of work will be going back to the heat engine, so that it will be self-sustained. Okay, so the net work output of this power plant is simply the difference between the total work output of the plant and total work input. So this is the formula. So W net out, okay, so this is the total net output of work equals to W out minus W in. So you will get the remaining work. Okay, so same concept. So the four components of the steam power plant involve mass flow in and out, and therefore should be treated as an open system. So that's the speciality of the system, because so you have mass going. So you have four systems here. So boiler system, turbine system, condenser, and pump. So from system 1, mass is entering to system 2. So we know when it involves mass in and out, it is open system or closed system. Mass in and out, open system. An open system, mass will enter and leave. So internally it can be considered as a open system, because mass from system 1 is entering system 2, and it can be also considered as a closed system, because all these things are inside a bigger system. So meaning it's a closed system, because all this mass is just a component of the larger closed system. So this component together with the connecting pipe, so you have a connecting pipes, always contain the same fluid. Okay, fluid is not increasing or decreasing, so it's always the same fluid, same like car. So you only change the engine oil, so engine oil will go around and come within the system. So generally it is still a closed system, because your engine oil is not going out of your car, so it's within the car, so it's going inside. Okay, so no mass enters or leaves this combination system, so it's a combination system, so it can be analyzed also as a closed system. Okay, so depends you as an engineer. So later on, when you are involving in this kind of situation, then you will need to see whether you need to consider it as an open system if you are investigating between these components, or you want to check the whole system, so you can consider as a closed system. Okay, a closed system undergoing a cycle, the change in the internal energy is 0. Okay, this is from the previous chapter. So if a closed system, internal energy is 0, because it's always within the system. Okay, energy is not going out of the system. So E in minus E out equals to changes in the system. So you can use this formula. So you just release. So because Q in, W in, so it's considered as input. So W out and Q out considered as output. So changes in the system is changes in all this. So change here supposed to be 0. Okay, so all these are 0 because nothing is going out. So all are 0. So you rearrange, so you can find the net output, the work. So that is how we calculate. Okay, in the actual system. Okay, so I am finishing with this. Okay, thermal efficiency. So we have studied about this in chapter 3 last part. Okay, efficiencies. Okay, so what is efficiency? So how much the heat is preserved. Okay, so like how I told earlier, the power bank. Okay, so if you constantly using the power bank, or once you charge by itself, the power is going out, but automatically is decreasing without you doing anything. So meaning the efficiency of the power bank is not good. So maybe the power bank is already spoiled. So you need to get replacement. So similarly, thermal is having the efficiency also. Okay. Uh, so Q out represent the magnitude of energy wasted. So earlier, a portion of heat energy is released to the sink. Okay, so we will consider the magnitude of the energy waste, and Q out is never zero. So you need to somehow you will have some losses. Okay, somehow, so it cannot be zero unless you have a very controlled environment where you make sure it's zero. But normally there will be some wastage. Okay, the net output of the heat engine is always less than amount of heat input. So meaning from the source earlier, so you let's say you're receiving 500 degrees Celsius. So when is going, whatever is converted as work will not be energy associated with 500. So maybe it's 450. So 50 degrees Celsius of work energy will be released as a heat. Okay, so thermal efficiency, the fraction of the heat input that is converted into net work output is measured of the performance of heat engine. So let's say you have a heat engine and you want to find the efficiency, so you need to use this formula. So like how we have seen in the chapter 3 last part, so normally all these formula are already calculated by engineers, so we just need to use. Okay, so if the question is saying is a turbine or is a heat engine, so normally we will give this formula. Okay, so you just need to know what value you need to put inside here to calculate the efficiency. So you will see the calculation questions at the end of the chapter. Okay, cyclic devices of practical interest such as heat engine, refrigerators and heat pumps operate between a high temperature medium, a reservoir at temperature TH, so high temperature, TH is high temperature, and a low temperature medium, so TL. Okay, so you can see, so these are some explanation, and this formula can also be converted to this. So QH is high heat, so equals to, so here is Q out, so here is low heat and over low temperature, so low heat energy over high heat energy. Okay, so this normally will be from the source, so this will be at the sink, so you can calculate. Okay, so we will study on all this tomorrow. Okay, so 10 more minutes, so I will just will tell what we will study tomorrow. Okay, so there are two things that we need to understand when we study about a second law. Okay, second law of thermodynamics. So there are two things that you need to understand. Okay, so this is a simpler way for you to understand. Okay, so the first one is high order to low order. So this is your first thing that you need to understand. So meaning naturally the temperature will move from high order to low order. For example, okay, so what I can give as an example? Yeah, cooking.
The smell from the kitchen to the
Okay, So normally the kitchen will be heated up. Okay, so the temperature will be higher because you are cooking, and because of the flow, so the flow will be starting from higher temperature zone to a lower temperature zone because of the pressure. So it can be example. So let's say I ask you to explain, so you can explain with the example. Okay, whatever example that you can relate. Okay, so another example, normally what will be so a cup of coffee that we have seen earlier. Okay, so let's say you have a cup. Okay, so you have a cup. Okay, so you pour coffee inside. Okay, coffee will be 70 degrees. Okay, let's say lah. Okay, 70 degrees Celsius, and the cup is, let's say, 20 degrees Celsius. So what will happen to the cup? So once you pour the coffee inside, okay, so if you see the cross section, okay, so you will have this. So let's say this is the so you have coffee inside. So coffee, so 70 degrees, and you have the wall of the cup. So 70 degrees, so here 20 degrees. So the heat will move from 70 to 20. It will never from 20 become 70 naturally. So that is what we call as a high order to low order. Okay, and another example that we can see, okay, maybe in this class. Okay, so I already learned about this. Okay, so I already have some knowledge on second law of thermodynamics, and you are newly exposing to second law. So I am teaching whatever I know. So I am considered like high order. So because I already have some knowledge, I am passing to you because you are learning. Okay, learning. So after this you can teach to others because your order already become higher than others. Okay, similar. So even you are working in a company. Okay, you will only work if your boss have money, right? Money to pay you salary, right? So will you work for a boss without money? Because you know your boss have money, end of the month he will give you. Okay, so similar. So higher order. So that's why you're willing to follow the instruction. Okay, so whatever works, job scope, so you are doing, at the end the company will pay you because the company has money, so they are considered as higher order. Okay, so we in the low order, so we will be receiving. Okay, so similar. So the world is operating this way, even nature. So nature, so is also operating the way, and it will only move from high order to low order naturally. So without so if it's something with assistant, so then it can go either way. Okay, so that's the first thing. The second thing is, okay, that you need to understand. There will be always losses. Okay, so no perfect system. Okay, because all of us are created not perfect. Okay, so there will be some losses some way along the way. So even the electrical power, so let's say you want to supply power 3 ampere from this point to this point, so along the way it will reduce a bit because of resistance. So the electrical charge can be converted into heat energy, and it will be having some kind of losses. So similarly, so let's say you want to travel from one point to another point, so your time will be converted, so your energy will be converted, so there will be wear and tear in your car. So something will happen that it will incur a small portion of losses. So it will never, you start with 500, finish with 500. Okay, so maybe it will be reduced to 470. So 30 will be considered as losses. Okay, so there will be always losses in thermal also, thermodynamics. Okay, so these two things are related to second law of thermodynamics, which we will be covering tomorrow. Okay, so you need to understand these two things. Okay, for you too. So if you understand these two things, you already can explain second law of thermodynamics. So because you already understand the concept. So how to explain? I will explain tomorrow. So it is based on Kelvin-Planck statement, and also got one more. Which is Clausius statement. So they have two statements. One will be covering this, one will be covering this. Okay, so any question? Okay, so no questions. So now time is, can you off? Stop the